Welcome back, guys. So, in the last video, we discussed the derivation of Otsu'S thresholding and we saw the summary of the algorithm. Okay, so today we are going to look at a mathematical implementation of the same algorithm, a problem, and we are also going to see the simulation of the same from Python. Okay, so let us first recap what we discussed. So, I'm going to the thresholding algorithm summary. Okay, so if you remember correctly, the first step was to identify the um, probability distribution of the image. So the probability distribution of the image is nothing but the histogram. So we compute the histogram of an image and then we normalize the histogram. So what is the formula for computing the histogram of an image? Yeah, so this is the formula for computing the histogram of an image, if you remember. So this is the first step. So in this step, we are going to calculate the histogram of the image. What is Ni? Ni is the number of pixels in the image that has the intensity I. Okay. So that is going to be Ni. We are going to add all the Ni values. For example, if L is equal to 4, okay, then what will this equation become? This equation will become N0 plus N1 plus N2 plus N3 because the range is 0 to L minus 1. If L is 4, then the upper limit will be L minus 1, 4 minus 1, which is 3. So what will be N naught? N naught will be the number of pixels whose intensity value is 0. Then what will be N1? N1 will be the number of pixels with intensity value 1. What will be 2? N2 will be the number of pixels with intensity value 2 and N3 will be the number of pixels with intensity value 3. So this is the first step in calculating the Otsu'S threshold. So let's go back to the algorithm. So we are calculating the histogram. The next step is to normalize the histogram. So how will we normalize the histogram? We have Ni. What we have to do? We have to divide Ni by Mn because we know how do we normalize any value? We divide it by the total number of values. So the total number of pixels here is given by M into N, which is the total number of pixels in the image. So to normalize the histogram, what will we do? We will divide all n values by mn, where m is the number of rows and n is the number of columns. So this is the first step. So what is the next step? The next step is to compute the cumulative sums P1 of k. So what is going to be the k value? In Otsu'S thresholding, the aim is to find out the optimum k. So what is k value going to be? The k value is going to be one of the intensity values present in the image, right? It is going to be an intensity value between 0 to L minus 1. So, to find out the optimum threshold in our problem, what we are going to do is we are going to calculate all these steps for all the k values. So, for example, if k is equal, you have L is equal to 100. Okay, that is the maximum intensity value. And you have a total of 10 different intensity values in the image. Then what we have to do in the Otsu'S thresholding problem, we have to follow or calculate all the next steps for all these 10 different intensity values. Okay, so that is how the system goes. So now, for example, if k is equal to 2, okay, we have to compute the cumulative sums P1 of k. So what is P1 of k? P1 of k is the probability of class 1. Okay, so what is class 1? Class 1 consists of all those pixels whose intensity is less than k. So let's go and check out the formula for P1 of k. So P1 of k is going to be nothing but I is equal to 0 to k Pi. This is the formula for calculating P1 of k. For example, if k is equal to 100, if k is equal to 100. How will this equation become? This equation will become all the values P0, So these intensity values should be present in the image. Okay. Though K is equal to 100, there are 10 different values, 0, 20, 50, 60, 70, and so on. Then those values will only be present in this equation. So P naught plus P10 plus P20, so on and so forth. Okay, what is this P value? I hope all of you remember what is the small p represents to. The small p represents to the normalized histogram. So Pi is nothing but Ni divided by m into n. Okay, that is how you calculate the cumulative probability of class 1. Okay, yeah. So we calculate the cumulative probability of class 1. Then what we do, we calculate the cumulative mean for all k values between 0 to L minus 1. So what are these k values? These k values are nothing but all the intensities present in the image. Okay. Hope that is clear to all of you. So what is M of k formula? Do you remember what is M of k formula? One second, guys. Let's go back to M of k formula. The simplified formula that we've seen. Yeah. So M of k or M1. M1 is mean for class 1. So it is going to be equal to summation I is equal to 0 to k I into P of I divided by P1 of k. Okay. So what is Pi? Pi is the normalized histogram value. P1 of k is the cumulative sum. Okay. Then how do you calculate the global mean? This is M1 is going to be the mean of the class, right? Then how do you calculate the global mean? M of k is going to be equal to summation I is equal to 0 to k I into P of I. This is the formula for calculating the global mean. So we have to calculate all these the cumulative mean, and this is the formula for calculating the global mean. Okay. So M of k, equation 8 calculates cumulative mean and equation 9 calculates global mean. So we are going to use these formula to calculate the next step. So we have calculated the cumulative sums. We have calculated the cumulative mean. Okay. Then finally, global mean. I told you already. We already seen equation 9 for calculating the global mean. Okay. The next step, we have to calculate the between class variance. So all these parameters, P1 of k, M of k, M of g, we calculated for calculating this between class variance only, because that is the ultimate concept of Otsu'S thresholding. We are going to choose that k value whose between class variance is going to be maximum. So we have to calculate this between class variance for all the k values. So how do you calculate sigma b square? We have the formula for that. The criterion for optimality. So this is the formula for calculating sigma b square. Sigma b square is equal to P1 into M1 minus Mg the whole square plus P2 into M2 minus Mg the whole square. You can use this formula, or we can go for the simplified formula. Mg into P1 minus M the whole square divided by P1 into 1 minus P1. Here we need not calculate P2. Okay, and we need not calculate M1 and M2 also. Only the cumulative mean and the global mean is enough, and also the probability of class 1 is enough. Okay, so this is a much simplified version of the formula. So we are going to use equation 13 to calculate the between class variance for all k values ranging between 0 to L minus 1. So that step is over. So what is the next step? We have to calculate the between class variance for all k values. Then what we will do? We will choose that k value for which sigma b square of k is maximum. Okay. We are going to use that k value for which sigma b square is maximum. That k value is going to be k star, the optimum threshold that we find using Otsu'S thresholding. Okay. So if this maximum is not unique, so what do you mean by this? If we do not get a single k value for which you have the maximum between class variance, what should we do in that case? We should choose all the k values or all the intensity values for whom the between class variance is maximum. And then what we are going to do? We are going to take the average of those k values. So this average value is going to be my optimum Otsu'S threshold. Okay. So now we have mathematically seen the concept of Otsu'S thresholding. Okay. So how do we say that this Otsu'S thresholding, or how do we prove that this algorithm actually works? So what I have done is I have created a simulation. Yeah. I have created a simulation using Python. Okay. We are going to see that simulation and verify if our O-source thresholding is actually giving us the optimum threshold. Okay. So I hope all of you are familiar with the Anaconda Navigator. So I'm using the Anaconda Navigator to call Visual Studio. Okay. I am using a specific environment. So this is the um, screen where we choose our environment of choice. Okay. So I have chosen my environment and now I'm going to launch my Visual Studio. Yeah. I'm launching my Visual Studio. So this is the code that I have written to understand the concept of Otsu'S thresholding. By now, all of you should be familiar with the theoretical implication, derivation, and the concept of Otsu'S thresholding. Okay. So now we are going to see if what we theoretically saw is actually correct. Okay. So what I'm going to do is I'm going to import the libraries needed to run my code. Now I'm loading the sample image. So I have taken the standard cameraman as my original grayscale image. Okay. All of you would be very familiar with this image. Now what I'm going to do is I am going to visualize the histogram of this particular input image. Okay. So we have already seen what is histogram. It is a plot of the number of pixel intensities present in the image versus the number of pixels present in each of these intensities. So as you can see, the intensity range in my cameraman image is from 0 to 250, and we have up to 5000 pixels belonging to every intensity level. Okay, this is the image histogram, and we use this histogram and convert it into the probability distribution that we need to find out the optimum threshold in Otsu'S thresholding. Okay, so now we are going to see the impact of using the correct threshold. What will happen if I don't use the optimum threshold? Okay, so I have created an interactive panel here. This is the original image. This is the histogram of the image, and this is the thresholded image that I have obtained after using the threshold of 128. You can see here. Okay, I have used the threshold of 128. So what will happen if I reduce my threshold? See, 83, 62. So what is happening? If I don't use a proper threshold, what will happen? I will lose lot of information present in the image. Okay. So now I am going for a higher threshold. What is happening? What is happening here? A lot of unwanted information is getting added to my image. More noise is getting added to my image, which is undesirable. Okay. So I hope it is clear to all of you how choosing an optimum threshold is very, very important for us to get the best segmented image. Okay, so from this itself, to some extent, you can identify if my threshold is somewhere in the range of 100, right, greater than 100, to somewhere between 120 or something, right? I'm getting the best result. This is what I have identified visually. Okay, also thresholding goes one step further. It tells us exactly which intensity level is going to work best. Okay. Yeah, so now what we are going to do is we are going to calculate the or use the Otsu'S algorithm to find the optimum threshold. Okay. Yeah, so I have used my Otsu'S thresholding. Okay. There are inbuilt commands. CV2.threshold gives you the Otsu'S thresholding. So I have used the inbuilt function to calculate the Otsu'S threshold, which is 102. So the Otsu'S threshold is 102, and I have used that particular threshold and achieved binary segmentation, as you can see here very clearly, right? Yeah. Now, what we are going to do is, I told you in Otsu'S thresholding, how do we calculate the optimum threshold? We go for the variance or the threshold that has got the maximum between class variance. So what I'm going to do is, I am going to calculate this maximum variance and plot this variance. See, look at this graph. So this graph I have plotted between threshold versus the variance. As you can see, exactly at 102, I have got the maximum between class variance. So our also thresholding concept is very, very clear. Is it not? So if I am able to choose, or if I choose a threshold for which my between class variance is maximum, then I will get the best segmented image. So we have practically proved that also segmentation works efficiently, right? So here I'm just going to show you an animated version of the graph just for us to understand. Program is running. Yeah. Now this is the animated version of our segmentation. Okay. So what I'm going to do is I'm going to run this animation. See, as the threshold increases, if it goes beyond our limit, it becomes very, very bad. Right? So exactly at 102, 100 plus, right? I get the best segmented reception. Hope the also segmentation concept is clear to all of you. So this cell is going to give me an interactive version of the between class variance graph. Okay. So this is just to show you that as the threshold increases, the between class variance increases. At one point, it becomes maximum, and then the variance again starts decreasing. Okay, if you compare this with our previous segmentation, what did you infer? What is between class variance? So, between class variance talks about the difference between the two classes, how easily it is how easy it is for us to differentiate between the two classes. So if the between class variance is maximum, it means that it is very easy to demarcate between the two classes. So as the variance decreases, differentiating between the foreground and the background becomes difficult. So the impact of variance over the segmentation is also very, very clear using this graph. Yeah. Now what we are going to do, we are going to compare manual thresholding versus auto thresholding. Okay. So manual thresholding, what should you do? I should keep checking various values of the manual threshold, replacing it until I get the ideal value. Okay. But in auto thresholding, it's a one-shot process and I get the optimum threshold mathematically. So here I'm just going to show you the bimodal histogram, the basic concept that we saw in thresholding, right? That gave rise to the concept of Otsu'S thresholding or thresholding as such. Okay. Finally, I'm going to give you a failure case demonstration. When does Otsu'S thresholding not work? Okay. One of the major places where Otsu'S thresholding struggles is when the illumination is uneven. So what do you mean by uneven illumination, the lighting is poor when you take an image. Okay, so what will happen if the lighting is varying over the image? One part of the image is dark, the other part of the image is light, then our entire Otsu'S thresholding is based on the intensity of the pixel. So if this is not going to be uniform, then what will happen? The Otsu'S thresholding will struggle and it will fail. So I have shown you one example. I have taken this particular image as my input. So this input or this image is called uneven thresholding, uneven illumination. So when I apply Otsu'S thresholding on this image, this is my result. As you can very clearly see, there is no output and Otsu'S thresholding has failed. So if the image is uneven illumination, then we cannot apply Otsu'S thresholding to it. Okay. Yeah. So hope this simulation gave you a clear understanding of the concept of Otsu'S thresholding. Okay. So now we are going to look at the mathematical implication. Okay, for simplicity I have used an Excel sheet to show you the concept, but in whenever you're presenting it as an answer for any kind of examination, make sure that you include all the formula and solve it step by step. Okay, so if you look at the first column, I have considered the gray level values 0, 1, 2, 3, 4, 5, 6 and 7. Okay, so these are my gray level values and this is Ni. So what is, if the number of pixels in the image that has a gray level 0 is 5. The number of pixels in the image that has gray level 1 is 8. The number of pixels in the image that has gray level 2 is 15. So this is the value of Ni. Okay, hope it is clear to all of you. This is the initial histogram calculation. Okay, what is the next step? The next step is to calculate the normalized histogram. So how do you calculate normalized histogram? Ni divided by Mn. So we should find out Mn. What is Mn? Mn is the total number of pixels. So here, how I have found out Mn? I have simply added all these pixels. This is giving me the total pixels as 84. So if in the question they give you M and N value, then you have to go for those values. What is M? M is number of rows. And what is N? N is the number of columns. So if that value is given to you, you have to use those values and calculate the total number of pixels and use that to normalize your histogram. If Mn is not given, then what you do? You simply add up all the number of pixels, Ni values, that will give you your total pixels. In this case, it is 84. Okay. Then what I have done, I have used Ni divided by Mn to normalize the histogram values. So this is your Pi. Okay, Pi is equal to Ni divided by Mn, small pi. We saw that, right? So these values are your Pi. Okay, next step. Next step, I want to calculate the cumulative sums. Okay, so what is cumulative sum? Cumulative sum, P of K formula we have already seen. Do you guys remember? What is P of K equal to? P of K is equal to the summation of Ni divided by Mn. The summation of the probability distribution. Summation I is equal, K is equal to 0 to L minus 1 Ni. Okay, Pi. So this, what is this Ni by Mn? எங்கிருந்து வருது? This comes from the normalized histogram. So simply for K is equal to 0, it is going to be 0.05952381. Okay, so for K is equal to 1, it is what it is going to be? It is going to be 0.05 plus 0.095. That is 0.15. Okay, for K is equal to 2, it is going to be the sum of all these three values, 0.333. Okay, for K is equal to 3, it is going to be the sum of all these values. So hope you have understood how the cumulative sum is calculated for all K values. As you can see in the last value, the sum of all the normalized histograms, what it is? 1. This also we have seen in the derivation, if you remember. Summation of Pi is going to be equal to 1. So that also we have got here. Okay, we have got the cumulative sum. So what is the next step? The next step is to calculate the cumulative mean. So how do you calculate the cumulative mean? M is equal to I into Ni by N. Okay, what is I? I is your gray level value. What is Ni by Mn? Ni by Mn is your normalized histogram. So you multiply that both and you get the cumulative sum of that particular class. So 0 into 0.05 is going to be 0. 1 into 0.09 is going to be 0.095, which is the cumulative sum of the gray level 1. Okay. Similarly, the cumulative sum of gray level 2, what it is going to be? It is going to be 2 into what is Ni by Mn? 0.17, which is nothing but 0.4523. So this is how we calculate the cumulative sum for all the gray level intensities. Okay. Next what you have to do, you have to calculate the class mean M of k. Okay, what is class mean? Class mean is summation I into Ni by Mn. Okay, so for example, for k is equal to 0, it's simply going to be 0. We have calculated I into Ni by Mn here for simplicity. Okay, so what I have done, I have calculated I into Ni by Mn for every gray level value. 0 into 0.05 is 0. So 1 into 0.09 is 0.09. 2 into 0.17 is 0.35. 3 into 0.2 is 0.7. So I into Ni by Mn I have calculated here. So this is class mean. So what it is going to be for 0, it is going to be 0 as such. Okay. And this is the class mean for k is equal to 1. This is the class mean for k is equal to 2. This is the class mean for k is equal to 3, and so on and so forth. Okay. Then what we are going to do, we are going to calculate the between class variance. So what is the formula for calculating the between class variance? If you remember, mg into p of k minus m of k the whole square divided by p of k into 1 minus p of k. So just to make the calculation simpler in the Excel sheet, I have split up all the formula. Okay. So I am calculating the numerator alone first. Mg into P of k minus M of k. I have calculated the global mean here. So what is global mean? Sum of all I into Ni by Mn is going to give me the global mean. So that global mean I am considering here. Mg into P of k. That is P of k cumulative sum. P of k is here. The global mean multiplied by P of k minus M of k, the class mean. Okay. That is going to be the numerator. The numerator, you have to square it. So I have squared it here. Okay. Then what I have done, I have calculated 1 minus P of k in this particular column J. And finally, what I have done, I have calculated P of k into 1 minus P of k in column K. Okay. So finally, I am calculating the between class variance. This is giving me the between class variance. Now look at the values I have obtained for between class variance. Does it resemble the graph that we saw when we simulated it in Python? So what is happening? The between class is increasing. It is becoming maximum at one point, and then again it is decreasing. Now at what point has it become maximum? So the gray level 3 is having the maximum between class variance of 2.06. Okay, so from this, which is going to be my optimum threshold, what is the value of the optimum threshold that I have obtained as a result of gray level thresholding? It is k is equal to. So now what I have to do, I have to carry out binary segmentation using k is equal to 3. So what is going to be my segmented image? All the values or all the pixels whose intensity is less than 3 is going to form one class 1. And all the values or all the pixels whose intensity value is greater than 3 is going to form the other class. So by using k is equal to 3 as the threshold, I am segmenting my image into foreground and background. Okay, this is how Otsu'S thresholding functions, right? So I have also shown you the calculation of one other factor called the separability measure. Okay, separability measure is actually you don't need that to calculate the optimum threshold. It is enough that you use the between class variance, but the separability measure is like reinforcing the concept again. Okay, separability measure is basically the between class variance of the class divided by the global variance. Okay, so the global variance I have calculated here, it is basically the square of I minus mg into ni by mn. Okay, so I minus mg. What is mg? Mg is your global mean. So I minus mg. Okay, I minus mg. What is I? I is your intensity level. So intensity level minus mg will give you this value. So we square it and then we multiply it with the normalized histogram. So this is the between or the separability measure. Okay. So the separability measure, yeah. So separability measure is going to be this value divided by this value, the global variance. The between class variance divided by the global variance. So the between class variance is given by these, the values in column L. So you divide that by the global variance. So we use these three columns M, N and O to calculate the global variance. Okay. What is the formula for global variance? N into Ni by M. And what is N? N is square of I minus Mg. So what is I? I is your intensity level and Mg is the global mean. Okay. So thus, mathematically, I have told you how to implement Otsu'S thresholding algorithm to find out the optimum threshold. Okay, so let me again repeat the steps. By now, all of you should be very familiar with the concept. We calculate Ni, we calculate the normalized histogram Ni by Mn, we calculate the cumulative sums, we calculate the class mean, we calculate the global mean, we calculate the between class variance. Okay, so the threshold value for which the between class variance is going to be maximum, or the intensity value for which the between class variance is going to be maximum. So that value is my optimum threshold that I obtain as a result of Otsu'S thresholding. Okay. Using that optimum threshold, what I can do, I can go for further segmentation. Okay. And finally, this is the separability measure. So separability measure is a dimensionless value. Okay. So it is basically used to reiterate or reinforce the result that you obtain from between class variance. Okay. As you can see, the separability measure is also maximum only for k is equal to 3, 0.669. So how do you calculate the separability measure? It is between class variance divided by the global variance. Okay. So between class variance, we already calculate. So how do you calculate between class variance? It's basically mg into p of k minus mk the whole square divided by p of k into 1 minus pk. Okay. Then what do? We calculate the global variance. So how do you calculate the global variance? Square of I minus mg. Okay. So what is I? I is the intensity value. Mg is the global mean. Okay. So we have calculated the global mean here. Okay. So then what do? Separability measure. It is going to be L2. What is L? The between class variance divided by the global variance for each case. So as you can very clearly see, we get the maximum separability measure again for k is equal to 3. So what we have done, we have effectively found out the optimum threshold for differentiation. Okay. Yeah. So hope the concept is clear to all of you. I just want to show you the simulation again once more so that you better understand the impact of threshold. Okay. Hope the concept of Otsu'S thresholding is clear to all of you. If you have any doubts, you can always contact me. Thank you.